This is a video for MEI Core Pure Mathematics, Second Order Differential Equations 1, Homogeneous Equations, 1.2, Auxiliary Equation Method for Second Order Differential Equations. So a reminder about second order differential equations. They are ones in which we have a highest derivative which is second order, and here that would be d2y by dx squared. Linear equations have all the powers of y and its associated derivatives of 1. In this example, we've got a dy by dx cubed, and therefore this is not a linear differential equation, and we won't be solving this within the context of these videos. So to find the general solution of this differential equation, we first of all form the auxiliary equation. And for this, d2y by dx squared is m squared, twice dy by dx is 2m, the minus 15y is just minus 15, and that's equal to 0. Now this equation factorizes. It's m minus 3 times m plus 5, which is equal to 0, which gives me two values for m. M is equal to 3, or m is equal to minus 5. Now I know that the general form for this is going to be y is equal to a e to the mx. That's what I'm looking at. Y is equal to a e to the mx. The problem being that I've got two values for m. So my general solution has two parts to it. It has y is equal to a e to the 3x. That's from the m equals 3 part, plus b e to the minus 5x. That's from the m equals minus 5 part. There is that written up more neatly for you. There's the auxiliary equation, which we go on to solve, which gives rise to two parts in the general solution. Okay, so what kind of curves do we get from that type of general solution? Here's a couple of plots, one with a equal to 0.2 and b is 0.3, and the other has a equals 0.2 and b is minus 0.2. And notice that the curves look very different, and this is down to the value of the two constants. However, there are some things in common. Notice that the intercept on the y-axis here and on here, well, here it's equal to 0.5, and here it's equal to 0. And in fact, when x equals 0, my intercept value will be a plus b. The other thing to look at is what happens for the behavior for x large and positive or large and negative. So as x tends to infinity, y tends to a e to the 3x. The bit with the e to the minus 5x will disappear as x tends to infinity. And as x tends to minus infinity, then y will behave like the b e to the minus 5x. And in fact, in here, because b is negative, that means that the curve shoots off towards minus infinity. Let's look at a dynamic plot for that. Here is that function with a equals 0.2 and b equals 0.3, so that's like the left-hand graph. If I drop this down to minus 0.2, you'll see that I get the right-hand graph. And if we look at what happens as we push this on up, if I pop this up to 1.8, then you'll see that a plus b equals 2 gives me the intercept on the graph. And as I alter my values for a, it continues to rise. When a is 1.2, for instance, the intercept will be 3, and so on. Now, the other interesting thing to look at is what happens as the signs of a and b change. If they're both positive, we get this U-shaped curve. If b is negative, we get this almost like a cubic curve. If it goes the other way, and a is negative and b is positive, again we get this curve that reaches between plus and minus infinity. And if they're both negative, then we get this U-shaped curve, but it's inverted. So the family of curves generated by this function are very much more complicated than we have previously seen for first-order differential equations. And partly that's down to the fact that we've got two parts to the function and we have got two different constants that we can alter depending on the boundary conditions. So in general, if we've got a differential equation, second order linear differential equation with constant coefficients of this form, then we can form its auxiliary equation, which is here, and then we solve that auxiliary equation. Now it's a quadratic, which means we can always solve it. The solutions may be real, may be repeated, may be complex, but we can always solve it. And what we've just looked at is what happens if I get two real solutions. So if I get two real solutions, let's call those lambda 1 and lambda 2, then I get a general solution which is of this form: a e to the lambda 1x plus b e to the lambda 2x. In subsequent videos, we'll look at what happens with different types of roots to this auxiliary equation. The next video in this sequence is 1.3, finding particular solutions given initial conditions.